Okay. Okay, let's start. Yeah, so now let's do the live stream now, right? This is lecture 20. Thank you for reminding me. And the warm-up problem is the following. It's a really simple matrix. It's a diagonal matrix. A is 1, 0, 0, 4. And the idea is to find eigenvalues and eigenvectors. So if you have already solved the problem, try a slightly more difficult one below. That is this A is 0, 1, 4, 0. I'm doing nothing but to swap the first column with the second column. Let's look at the problem, okay? For the first one, so it's the R2. So we can first look at what this matrix does geometrically. So geometrically, what it does is you have, this is X, this is Y, or X1, X2. If I take X1, which is 1, 0, A just makes X to be the same thing. Or E1, and AE1 is just E1. If I take the other vector, which is called E2, or 0, 1, and then this diagonal matrix is going to amplify that to 4 times E2. You see that this E1 and E2, they're automatically eigenvectors. Why? Because they satisfy the relation AV equals to lambda V. That is, after applying A, it only changes the length of the vector, but not the direction of the vector. So more formally, we have A times 1, 0 equal to 1 times 1, 0, and A times 0, 1 equals to 0, 4. And therefore, the eigenvectors are, and the 1, 0, and 0, 1. But of course, if you scale any of the vectors, that would work as well. So if we look at the second one, that is a lot trickier. I mean, I can also try to do the same thing, but I found that 1001 definitely doesn't work because I apply it to 10, I get a 04, so the direction has completely changed. As we said last time, we can make a guess. It's not a very systematic method, but once I tell you the answer, it is very easy to check whether a given vector is an eigenvector or not. In this case, I'll just tell you the answer. So the first one could be 1. Let's check this 1, 2. Seems to be a very educated guess, but once I tell you, then this is 0, 1, 4, 0 times 1, 2. So this one is, this is 2, this is 4, and this is equal to 2 times V1. So indeed, I got an eigenvalue that is, this is V1 is eigenvector with eigenvalue lambda 1 equal to 2. Okay, there's someone, Matthew raised a hand. What's the question?
In the first example, are the two eigenvectors that we found the only eigenvectors or just two examples of eigenvectors?
The question is whether these are the only two eigenvectors. It's a very good question. First of all, they're not the only two eigenvectors per se, because if I change 1, 0 to 2, 0, that's also eigenvector, which is obviously different from the original eigenvector. So you cannot just say, 1, 0 is the only eigenvector because there are infinitely many others. But you can also say up to linear dependence relation, whether these are the only two eigenvectors. The answer is yes, and we're going to answer these questions later. Any other question? Good?
What is the eigenvalue for the first example?
Oh, okay. So the eigenvalue for the first one, so this one is 1, and this one, the eigenvalue is 4, because this is equal to 4 times 0, 1.
Okay, thank you.
Good? Okay. So I guessed, so this is the first eigen vector. Now I want to find the second one. I don't know whether there exists a second one, but again, now I make a very educated guess. I have no idea how I came up with this, but again, once I tell you, I can readily check whether this is true or not. And this one is, so so this is -4 plus 2, so this is -2, and then the second one is sorry, so this one is 2, and this one is -4, right? -4 times 0, and therefore this is -2 times -1, 2. So V2 is indeed an eigenvector with eigenvalue that is -2. And we found the two eigenvectors by brute force computation, but we have no idea how we actually came up with these vectors. So it is really the central topic of this class, which is I give you a matrix. How do I find all the eigenvalues and eigenvectors? So how to find eigenvalues and eigenvectors systematically. Good. So recall the definition. The definition of eigenvector V associated with eigenvalue lambda is this linear relation AV equal to lambda V. As we talked about last time, the idea is that AV does not change the direction of V. We only have two vectors, and therefore they are linearly dependent. So this is the only possible relation to characterize this relation. So we start from this definition and move the right-hand side to the left-hand side. So this is equivalent to A minus lambda times identity V equal to 0. And here eigenvector a zero vector cannot be an eigenvector. So V is not 0, which means that it's a non-trivial. And here I'm using the word non-trivial precisely with respect to the solution of homogeneous linear system, because this is really some A tilde x equal to 0. So this means for this A tilde, the dimension of the null space is actually not 0. What does it mean? It means that A minus lambda I, this matrix, is not invertible. Because if it were invertible, then all the columns should have a pivot, then A minus lambda I V equal to 0 only has trivial solution. This is very important. Any question? Okay, so if it is not invertible, then as we just learned in chapter 3, this is really why I want to switch the order between the chapter 3 and chapter 4. Chapter 4 is a lot closely related to chapter 2, and chapter 3 is a lot more closely related to chapter 5. So we just learned that if a matrix is not invertible, then there is an identity that is the determinant of A minus lambda I equal to 0. I don't know what the value, how do I find lambda at this point, but I do know that if lambda is an eigenvalue, then the determinant A minus lambda I should be 0. And what's the determinant? So it looks like this. So this is something like A11 minus lambda, A12, A1n, da da da, AN1, da da da, ANN minus lambda, so equal to 0. Now I try to do a cofactor expansion. Cofactor it. I do a cofactor expansion, it looks like A11 minus lambda times C11 plus A12, C12, da, 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 A1n, C1n equal to 0, where, to be clear, that all these cofactors, which are determinants themselves, also depends on lambda. So now I have a non-trivial statement, which is this guy, okay? It obviously is a function of lambda, but this is not some arbitrary function of lambda. It is actually a polynomial of lambda.
Sorry, what does the blue say, like after C11?
Oh, parenthesis lambda. So
Oh, okay,
just say
thank
it
you.
depends on lambda. Yeah. So this is a polynomial of lambda. And it's not only an arbitrary polynomial of lambda, but a polynomial of lambda up to degree n. It's a polynomial of lambda of degree n. Why this so? Is because of the following. You look at the cofactor expansion. I'm expanding that. So this guy is lambda, the first power of lambda. I cross this. This is nothing. So this is C11 lambda has exactly the same structure, but with one row and one column less. So I can say do induction, if you remember the inductive definition of determinant. I don't know how to define the n-dimensional, the determinant of an n-dimensional matrix. I assume the determinant of n-1 dimensional matrix has already been defined and then expand, right? So I assume this is true, which is the polynomial of this one is indeed a polynomial of lambda of degree n. This is of degree 1, and this one is, by assumption, is a polynomial of degree n minus 1, sorry. Multiplied with this, it is a polynomial of degree n. This one, A12, is a number. Now, C12 lambda is at most a polynomial of degree n minus 1. I just add them all together. So this is still a polynomial of degree n. Is that clear? This is degree 1. Okay, so this equation, determinant of A minus lambda I equal to 0, it must be of the form Pn lambda equal to 0, and this one we just find all its roots. And we get the eigenvalues. If this is the first time you see it, it might be horribly counterintuitive, but we're gonna just work with a few examples and to see that at least for low dimensional matrices, this is not hard at all. And then we're gonna talk about how do we find the eigenvectors. Any question? Okay, so let us look at examples. So A is 1, 2, 2, 1. And I have lambda, so I want to solve this. So I have A minus lambda times I2. So this is 1 minus lambda, 2, 2, 1 minus lambda. Now I consider the determinant. And this is multiply. This is AD minus BC. And this one is, this is equal to lambda squared minus 2 lambda minus 3. I can factor it. So this is lambda minus 3, lambda plus 1 equal to 0. This immediately, lambda minus 3, yeah. So this immediately tells me that the first root is lambda equal to 3. The second root is lambda equal to minus 1. And these are all its eigenvalues. Because if lambda were an eigenvalue of A, it must satisfy this equation. There are only 2 roots, so these are the only 2 possibilities. Is that clear? Okay. So now we want to find the eigenvectors. How do we find eigenvectors? Remember, at the beginning of this class, I first gave you the eigenvector, and then just by straightforward matrix vector multiplication, I checked and found the eigenvalues. Now, the method I just showed you is to solve a quadratic equation and find the eigenvalues. Now I need to find the eigenvectors. But this is very easy because once I know what eigenvalues are, then V is the non-trivial solution. Maybe there's more than one. The solutions of A minus lambda pi V equal to 0 is that you might say that, wait a minute, we're back to square one. I mean, you, at the beginning of this, you really started saying this. But there's a huge difference because now, after solving the polynomial equation, this is known instead of saying it was an unknown number. So I can just loop over all the known eigenvalues and solve this equation. Let's say for lambda 1 equal to 3, I want to solve which equation? So it's A minus lambda. A was 1, 2, 2, 1. And so this is A minus 3i V equal to 0. So this is a matrix. This is a very well-defined matrix, minus 2, 2, 2, minus 2. So this is A minus 3i. And V equal to 0. Now we're back to chapter 1 again. So as I said, the whole linear algebra part of this class is we learn fancier and fancier stuff, and then in the end reduce to chapter 1. So I found the eigenvector, which is 1 and 1. Now you have found the eigenvector. You can use the method at the beginning of the class and just plug in and multiply AB. You will find that it should be equal to 3B1. That will be left to be as an exercise. Any question? The same way, we do lambda 2, which is minus 1. And now I have A plus I, V equal to 0. So this matrix is 2, 2, 2, 2. V equal to 0. So this one just gives me V2 equals to 1 minus 1. Then we're done. We have found V1 and V2 are linearly independent. They already span R2, so it's impossible that there is a third linearly independent eigenvector. Another way of viewing that is we have found all the possible eigenvalues, and a necessary condition to be an eigenvector is to satisfy this equation. For this equation, we have found all the solutions, and therefore that's it. Okay, so
Quick question.
yes.
So would you say that the number of eigenvalues will always equal to the number of eigenvectors?
Okay, so the question is whether the number of eigenvalues will always equal to the number of eigenvectors. That's a very good question. Let's just ask it now. So let's write down. So question is the number of eigenvalues always equal to the number of eigenvectors. So the example above obviously showed that this is possible, but the question is whether this is always the case. Let's take a look at the one example. So A is 1, 0, 0, 1. Okay. So, I mean, I can just apply the same method above, but let's just apply the method above to be absolutely sure this is true. So A minus lambda I, so this is A1 minus lambda, 0, 0 minus lambda, this is 1 minus lambda squared, and this is equal to 0. We found that I only have one eigenvalue, and what are the eigenvectors that are linearly independent? So this should satisfy A minus lambda IV 0, but this is just a zero matrix. I can take two arbitrary vectors, let's say 1, 0, 0, 1. So there are both eigenvectors. Therefore, the number of distinct eigenvalues is not necessarily always equal to the number of eigenvectors. Did this answer your question?
Yes, and then
Okay.
one more quick question.
Yeah.
So when you go for the eigenvalues, do you ever need to check whether the root is valid?
You do need to check. Yeah. So I mean, this is the universal method to find the eigenvalues. It should satisfy that the determinant of A minus lambda I is 0.
Okay, thank you.
Yeah. Okay, you're welcome. So, well, you might say that it's a bit unfair because, I mean, lambda equal to 1 does not just mean that there is only one eigenvalue, right? I mean, you can also count multiplicity. Because I can have two repeated eigenvalues. In this case, the multiplicity of the eigenvalue is 2. So you say, well, the counting multiplicities, the number of eigenvalues indeed matches the number of eigenvectors. So the question needs to be further refined. Question, let's say this is question 1. And the answer is no, right? The example is below. Now let's refine this question. Is the number of eigenvalues counting multiplicity? If it is a repeated eigenvalue, I count it as 2. Always equal to the number of eigenvectors. I think that's a fair question. Okay, so that one, is there any question?
What do you mean by multiplicity in this
Well,
case?
multiplicity just means that, I mean, this solution, so if I factorize a polynomial and let's say lambda minus 1 squared, so that one should really be viewed as lambda times 1, lambda minus 1 times lambda minus 1. So I have two roots, lambda 1 equal to 1 and the lambda 2 equal to 1. So these are, I mean, think about if this is not 1, but 1.01, right? And you would have two roots. It's just that I take this 0.01 to be arbitrarily small, and therefore they become the same root. So this is called a repeated eigenvalue, and or mathematically it's called lambda equal to 1 has a multiplicity 2. Make sense?
Yes, thank you.
Any other question? Okay, so now this is a harder question, but I think it's a fair question because indeed, if I just say this is a 1, 0, 0, 1 plus epsilon, epsilon is an arbitrary small number, and I mean all the way along the way, I mean 1, 0, 0, 1 all the eigenvectors. If you just say the limit 1 epsilon goes to 0, it doesn't make sense. I mean the question seems unfair. So let's try to find another kind of example. So this one is the following, which is A is, let's say 2, 1, 0, 2. Okay, pretty innocent matrix. And we use the same method as before. A minus lambda I. This is 2 minus lambda, 2 minus lambda, 1, 0. And this is 2 minus lambda squared minus 1, 0. And oh, sorry. There's no minus 1. 2 minus lambda squared minus 0 times 1, so 0. So I found that lambda equal to 2 is an eigenvalue, and it has multiplicity 2. Okay. So now let us find the solution, find its eigenvectors. Let's see whether, as before, we can find two linearly independent vectors. So this means that corresponding eigenvector B satisfies 0 here, 1, 0, 0. B1, B2 is 0, 0. You say, wait a minute, before I subtract 1 here, I mean, there's no pivot whatsoever. So the dimension of the null space is 2, and that's why you could find these two eigenvectors. Now, this is obviously a pivot. So the dimension of the null space by the rank theorem, remember, rank theorem is a trivial statement saying that the number of columns equal to the number of columns with a pivot plus the number of columns without a pivot. So there's already a pivot, so the dimension of the null space can only be 1, and the solution is 1, 0. So I okay, so instead of chatting, can anyone just unmute yourself and ask the question? Because it's really hard for me to talk while seeing the chat. Any immediate question? If it's just a question sharing between yourself, you don't need to share, share it to everyone. I think there's maybe an option for you to, let's see. Welcome to Berkeley Math 54. Reflects our muscles and our typing. Okay. No. Not exactly. Okay. I take this as a sign that there's no immediate question. So you see that. So you see that this V, there's only one eigenvector, Where's the other one? I mean, this is the only possible eigenvalue, and we have only found one eigenvector. So a more precise statement is, I mean, of course, you can, once you find one eigenvector, means there are infinitely many eigenvectors. I can just change this to be 2, 0, 3, 0. But what it means is I couldn't find two linearly independent eigenvectors. What's going on? So this one we need to study. We'll study a little more systematically later. But for the moment, let us just say that we have concluded using a concrete example that the answer to Q2 is also negative. Any question? Okay, so yeah.
For the case where the matrix is the identity matrix, is the number of eigenvectors infinite? Since you would get whatever you
the
find?
eigenvectors, as long as you can find one, it will be formally infinite. Therefore, a more precise way of talking about that is you can only find two linearly independent eigenvectors.
I see. Okay, thank you.
Okay. So, so let us now work on another example. So, so A is 0, 1, 1, 0. Okay, and I mean, now we have worked on this for a few times. I can simplify this a little bit. So this is minus lambda. This is 1. This is 1. This is minus lambda equal to 0. So this is lambda squared minus 1. And therefore, we have lambda 1 equal to 1 and lambda 2 equal to minus 1. So, what it means is that for lambda 1 equal to 1, we try to solve the linear system. So this is minus 1, 1, 1, minus 1. V1 equal to 0. Immediately we solve. V1 equal to 1, 1. Okay. And for the other one, lambda 2 equals to minus 1. And this is, so minus 1, so it becomes 1, 1, 1, 1. Very similar to the example we had before, 0. And this is V2 equal to 1 minus 1. So pictorially, what it happens is the following. So I have a 0, 1, 1, 0. And so what it does is to reflect it just applied to E1 and it becomes E2. If you apply E2, it becomes to E1. So it is obviously doing a reflection around the x equal to y line. And if there's a reflection geometrically, then this line x equal to y will be an eigenvector because it just stays there, it doesn't move. This is exactly V1. So it's a reflection and this V1 doesn't move and it corresponds to lambda 1 equal to 1. On the other hand, I have this V2 that's also special because after reflection, maybe I should use a different color. After reflection, this becomes minus V2. This is exactly this. So it is rather intuitive why this V1 and V2, they are eigenvectors, because after applying A, only the direction changed, but not its, sorry, only the magnitude changed, but not its direction. That means that didn't go out of the line. Okay, so this seems to be very straightforward. So let's look at a very related example. So this is 0, this is minus 1, 1, 0. Okay, so compared to the example before, I have only added a negative sign there. So look at this. So what is this doing? Let's first look geometrically. if I start from E1, and AE1 would be so 1, 0, and it would become 0, 1. So this is 0, 1. So this becomes AE1. It rotated 90 degrees. Now, if I start from 0, 1, it will become minus 1, 0. So if I start from E2, then it will be rotated. This would be AE2. So it's minus 1, 0. So you see, this one, instead of a reflection, this A matrix, although the only difference is a minus sign, this is a rotation. As we talked about briefly last time, not all matrices can necessarily have eigenvectors, because I mean, the definition of eigenvector is the direction doesn't change. But if I rotate every vector by 90 degrees, then it's impossible that I will find a vector that applying A, it doesn't change the direction, right? I mean, it by definition changes the direction. Nonetheless, let us try that we just apply the same machinery, what we will actually find. So this is A minus lambda I. So this is minus lambda minus 1, 1 minus lambda. So this is lambda squared plus 1 equal to 0. Compared to before, it was lambda squared minus 1. So this one becomes plus 1. Now we know lambda 1 is plus I, and the lambda 2 is minus I, where I is the imaginary unit satisfying I squared equal to minus 1. So you see, indeed, if I want to restrict everything to real arithmetic, this is not possible. But this rotation matrix actually has an eigenvalue that is complex. So this is complex eigenvalues, even though this matrix A is a real matrix. Let us now find the eigenvectors. Lambda 1 equal to I. So the null space is, so this is minus I minus 1, 1 minus I. And I want to solve V1. I want to solve V1 equal to 0. Leave to you as an exercise. It's a very simple thing to do. And this one is I1. Why? Because minus I times I is 1, minus 1, so this is 0. I minus I is 0. So indeed, this is true. The other eigenvalue is minus I. This is I1, 1, I. V2 equal to 0. And this is minus I1. So we have indeed found, again, two linearly independent eigenvectors corresponding to this matrix. Any question? Okay, so now we have said, using a few examples, that for two-dimensional matrix, 2 by 2, and we can find, sometimes we can find two linearly independent eigenvectors, but sometimes, as the example before showed here, you can only find one eigenvector. We restricted to dimension 2 purely for simplicity, because if, let's say, we want to do a 5 by 5 matrix, unless the matrix has some special structure. We will need to compute 5 by 5, make the determinant for a 5 by 5 matrix. According to the homework you have done in chapter 3, you'll find this is actually not a very simple issue. So, but nonetheless, we can talk about general n by n matrices. You give me a matrix A, which is of size n by n. If we can find n linearly independent vectors v1, vn, such that avi equal to lambda I vi. This line means that all the v's are eigenvectors. Someone was annotating on my, wait a minute. If someone, probably I should stop the annotation on the screen, but if someone annotated, could you erase that? Thank you. I'll try to disable the guest annotation next time. I didn't know that. So, any question? Okay. So that means each vi is an eigenvector. Then A is diagonalizable. Okay, A is diagonalizable. Why is called diagonalizable? As we said last time, this equation can be reordered into AB equal to V times D, or D equals to V inverse AV, where V collects all the vectors. D is a diagonal matrix consisting of the eigenvalues. So after this V inverse V operation, A is diagonalized into diagonal matrix, so it is called diagonalizable. And this lambda i's could be the same, could be different, I don't care. As long as there exists such lambda i's, then I'm fine. So we have seen examples that previously A is 2, 1, 0, 2 is not diagonalizable because we could only find one instead of two linearly independent eigenvector, and all the other examples we have studied before, including the rotation one, they are diagonalizable. Now we want to ask the question Q3. Let's recall that what was Q1 and Q2? Q1 was saying, is the number of eigenvalues always equal to the number of eigenvectors? The answer is no. Q2 is the number of eigenvalues counting multiplicity always equal to the eigenvector? Now, using the language we just introduced, this Q2 was actually saying, are all matrices diagonalizable? The answer is no. Now, we change from being super optimistic to super pessimistic. Question Q3. Is there arbitrarily large non-diagonalizable matrix? We have known that in this 2 by 2 matrix, this is the case. Is there for any given n, whether there is a matrix of size n by n that is not diagonalizable? This seemingly super pessimistic question, the answer is yes. 0. For any n, there exists a that is of size n by n, not diagonalizable. This example is actually very much characteristic, and I hope you can understand. The proof is constructive, which means that I'll just give you an example. I'll directly construct such a matrix, which is A equal to this. For any lambda, that is R, or C, that's fine. I put lambdas on the diagonals, so there are n rows. It's upper triangular matrix. I have a huge 0 block in the entire off diagonal. It's very special. The first off diagonal thing, I put a 1 there, and again there's 0. So example. So I have lambda 1 0, lambda 0 0 0 1 1 0, lambda 0 0 0 0 0 0 1 1 1 0 0 0, so on and so forth. Okay, so there are only 2 diagonal lines that are not 0. Diagonals can be anything. Here's as well. By scaling argument, you can put anything here, non-zero here as well. I claim this is not diagonalizable. If the claim is true, because the dimension n is arbitrary, I've proved the theorem. I just found this A. So I just compute it. So A minus lambda I. So this is sorry. So I've already used the lambda. Let me say lambda prime. So this is lambda minus lambda prime. Lambda minus lambda prime 1 1 0 0. This is upper triangular. So this is lambda minus lambda prime to the nth power equals 0. This means that the only possible eigenvalue, lambda prime, is my given lambda. There's no other possibility of multiplicity n. Let us now find the eigenvectors. The eigenvector satisfies the following equation. 0, 0, 0, 1, 1, 1, v equal to 0. Now you see, this is a pivot, this is a pivot, this is a pivot. So the only free column is this. So the dimension of the null space of this matrix is 1. So I get V, there's only one eigenvector, is 1, 0, 0, 0, and that's it. So what I showed was actually a little bit stronger than what the theorem suggests. Not only I have an arbitrarily large matrix that's not diagonalizable, where there's a maximal discrepancy between the number of eigenvalues counting multiplicity and the number of eigenvectors. So we have only one eigenvector. Any question? If not, I think thumbs up, and I'll see you virtually on Friday. Stop the sharing.